Hey, Vlad here, devinsider.com. Welcome to another video. In the previous few videos, we spent quite a bit of time overcoming the challenges with recursion. We wrote an algorithm and then we rewrote it into a version that allowed the Scala compiler to eliminate the tail calls and thus simply to rewrite it to a regular loop. And if that was not possible, then at least we moved the computation from the stack to the heap, which is drastically larger, even if the memory that the JVM is allocating to the stack was maxed out. Then in the previous video, we started playing with continuations, which don't seem to have problems with recursion because the computation always goes forward, and therefore the last call is always the call to the continuation, and therefore the continuation is by definition in the tail position. Today we're going to dive a bit deeper into the interplay between stacks and continuations, and we will also use continuations for something entirely different. Alright, grab some popcorn and let's get started. As always, we're in the Ubuntu virtual machine and we're running a Sublime with a plugin called Terminus, which emulates a regular terminal for us. Inside of this terminal, we're running SPT, and we can run our main, the one where we left off from the previous video, or we can run our tests, and the test will be rerun every time we save the file. Now, as in most videos recently, we're going to start with a tiny refactoring because there are always like one or two things that I've forgotten. So the first one is in the stacks. By the way, it's still compiling to run the test. There we go. So in the stack, I accidentally had a spelling mistake over here. So it's not peak, it's peak. And let's see if we're using it anywhere. Yeah, we do in Fibonacci 35. There we go. Peak. All right, and the next one is going to be Fibonacci itself. At the top, I commented out extends app. I actually want to have multiple apps. Sorry, I wanted to do that. Extends app like this. And also we had a tiny bug over here where we have a Fibonacci, the original version of Fibonacci, but it's calling another one. It was supposed to call the original one. And because we don't want that to happen again, we're also going to go to this one, this Fibonacci one, which was the last one, and we're going to call it Fibonacci tail rack stack. Fibonacci tail rack stack, like this, like that. There we go, and this is all that we need for today. So what I'm going to do now is I'm just going to press that so that we can just see git status. By the way, notice Terminus has some sort of bug that it colors that stuff blue and only the last characters in white. It's kind of weird. Anyway, git commit happen.im video 15 refactoring and other improvements. What the hell was that? All right, I'm going to push in the end of the video, so we can close that, and that's all that we needed for today. All right, so what we're going to do today is we're going to write a bunch of versions of the Fibonacci algorithm, and because by the end of the video we're going to end up with quite a few of them, we need to make our print lines a little bit more fancy. Oh, by the way, now it tells me that there are two mains, so instead of just running, we have to say run main homegrown collections Fibonacci. All right, so we constantly want this one, and we don't want to select anything. All right, so what we're going to do is we're going to instead of this just going from 0 to 10 and mapping everything to log and then mapping them to only one of these, because right now we have three of them, right? We have the original Fibonacci, we have the Fibonacci tail rack. Hold up, I can actually do that. Right, and we have Fibonacci tail rack stack, right? So what I want to do is I want to be able to run all of them, so we're going to improve that line basically. So we're gonna have a sequence of Fibonacci functions, right? So I'm gonna call it Phoebes, and a Fibonacci function that takes along and produces along, right? So I'm just gonna have a sequence, and I'm gonna put all of them inside, right? So I'm gonna put this one in, comma, this one, comma, and this one, right? And also we're going to change that part. So we're going to go from 0 to 10 as before, but this time it's going to be like that. And I'm going to use the dot notation, which is preferred, by the way, instead of the operand notation. So we're going to take every number here, right, from 0 to 10, every number, and we're going to produce a tuple with that number on the left, and on the right we're just going to run the Fibonacci's, right? So we have the sequence of Fibonacci's, we're going to map them. So this is the Fibonacci functions. We're just going to apply them to n. So By the end of this, we're going to have a list of tuples. On the left, we're going to have the number, and on the right, we're going to have a list of results. Okay, so we're going to map it again. So we have the n and we have the results. If I could spell results like that. Okay, scroll down a bit. Okay, so what we have here is we're gonna make sure that all of the results are the same. So we're gonna and then if they're not, we're gonna display this line in red, and if they are, we're gonna display the line in green. So the first thing we need to do is we need to determine the color, and we're gonna say if are all elements equal, and we're gonna write this function in just a second. Then console.green, otherwise console.red. And then we're going to produce a row, and we're going to prepend the number itself to the row, right? So not the results. So we're going to have the results, and they're going to start with an n. We discussed this in a few videos ago, maybe even in the previous video. I don't actually remember that the methods that are ending with a colon are right associative, right? So we're calling this is a sequence of results. So we're calling this method on the sequence of results, and we're passing this as an argument. So we're prepending n to the results. Right, so we have that, and then we're gonna have make string, which is gonna insert just a tab character. All right, so now we're gonna have color plus row plus console dot reset, and now that we're done, we're just gonna print out everything that we have. So unless I've forgotten something, forgotten to implement this. My Sublime unfolded all of the Fibonacci's that are collapsed before. Let's remove that, and let's introduce this function, right? So it says that we're missing this function, are all elements equal? So let's just have it over here. So what comes in as an argument is the results, which is a sequence of long, produces a boolean, and we're just going to match on the result. And I'm going to say, okay, if that's an empty sequence, then just return true. Otherwise, deconstruct the sequence into the head and into the tail, like that. Then ask the tail if every element in the tail is the same as the head. And that's all that we need. And unless I have created a few spelling mistakes, no, I haven't. All right, so this is what we have. And if one of our Fibonacci functions is doing something weird, for example, I don't know, let's make it 2 over here. All right, see, then we see that, which one? This one was wrong. So starting from here, right? So from here, every result was wrong all of a sudden because we had a mistake. All right, so this is what we need in terms of print lines. So now we're just going to continue writing different versions of Fibonacci's. All right, so let me minimize that a little bit like this. Okay, so what do we have so far? We have the original version of Fibonacci, then we have the tail recursive version of Fibonacci, and then we have the tail recursive version of Fibonacci, which uses the stack to carry the number itself, right? So we pretended as if it wasn't possible to rewrite Fibonacci in a tail recursive way, like this, right? And we use the stack. So what we're going to do now is we're going to use the stack not for the number, but we're going to use the stack to carry the accumulations. And it's going to be pretty silly and very unnecessary, but it's going to help us to make the jump to continuations. And before we do that, let's also rewrite this one real quick. So I'm just going to copy this one, the tail recursive one. I'm just going to do a 2 over here. So what I want to do here is I want to carry the first accumulation and the second accumulation in a different order, right? So I want to say that this is the second one and this is the first one. It's completely unnecessary. It's just going to help you to understand the version with the stack a bit better, right? So this is going to be the second one and this is going to be the first one. Now, because we're using named arguments, we don't have to move anything here, but still I'm going to do this just for clarification purposes, right? So this is how I want to have it. Again, it looks completely unnecessary. And look, now I can just go over here and edit over there, and it's just going to run it for us as well, right? So everything should still be the same. Everything is green. All right. So what we can do now is I'm going to leave that one like sort of at the bottom. Or actually maybe I shouldn't. No, I'm going to leave it at the bottom. Okay, so the one that we're going to write next is, I'm going to copy that again. This one over here. Okay, so I'm going to call it Fibonacci tail rack stack ACC. So we're going to use the stack to carry these accumulations, right? So instead of carrying the 2 and 1, what we're going to do is we're going to have a stack long. Okay, so because we're carrying the stack like this, we need to push these 1 and 0 over here, right? So I can kind of create an empty stack, and we're going to push. And we're going to help out the type inference a little bit, because what we're going to go push is an integer, but we want actually long. So we're going to do this, and we're going to do that. And this is exactly why I reverted them, because I knew that for the version with a stack, I would need to push the 1 first. Okay, so now that they're pushed, the first thing that is happening is we need to retrieve them, right? So we need to get them out of the stack. So what we're going to do is we're going to deconstruct the stack like this, not empty. First accumulation, comma. And I'm going to continue writing here, but I know that the formatter is going to ruin this for me. So I'm going to do this, and I'm going to do that, right? So now I can format things as I want over here, right? So we're deconstructing the stack. We're assuming that there are always at least 2 elements in there, because we know that, because in the beginning we'll push 2 elements in there. So it's going to be non-empty, and this is going to be the second one. And over here we're going to have the rest of the stack, but we're going to see in quite a bit that we actually don't need this at all, right? So what we can do right now is we can do rest of the stack. We can take it, and instead of manipulating like these 2 variables, which we don't have anymore, we have just a stack, right? So what we need to do is we need to take that, and we need to push first this. This is exactly why I reverted them, and then that, right? And unless I did some silly mistakes, it should be fine. Let's see if it compiles. No, it doesn't. What's wrong? Oh yeah, of course. I forgot to actually give it something to deconstruct, right? So we're taking the stack, we're pattern matching on it. Remember in the video about pattern matching, everything that is between the val and between this equal sign is a pattern match case, is a pattern, right? So we're taking the stack, we're pattern matching if it fits this pattern, right? If there are 2 elements and some rest of the stack. Okay, so now it should compile. Yep, it compiles, but we're not running it yet. Let's run it. So where is it? This one. Okay, so let's add it over here, right? Okay, so the results are the same, but they're the same because we only care about the very last 2 things on the stack. So we don't even need the rest of the stack. So we can start with a stack empty, or we can start with, you know, it doesn't really matter, because we only care about the last 2 things on the stack. So in fact, the last thing that I'm going to do is I'm going to have an underscore here, right? Because we don't really need it at all. Okay. By the way, if you're following this at home and you want to try it out, the whole thing is going to be on GitHub. And what you can do is you can go over here and you can say, okay, I just want to see the Fibonacci of 10. So you generate a range from 10 to 10, right? So it will generate only one result, right? Which is 55. And then you can go over here where you have the stack, for example, over here, right? So the stack comes in, and what you can do is you can print out the stack and see what's on the stack. So because we're doing this thing only once, you can see exactly, okay, this is what was on the stack: 0, 1, 1, 1, 1, 2, 2, 3, 3, 5. So I'm gonna remove the print line, and I'm gonna go back to running all the 10 examples. Okay, so let's go back, and so what we can do now is we can see how continuations can do what the stack did here for us, because we're going to use the continuations in this position and not in that position. So the first thing that we're going to do is we're going to go to CPS, and we're going to copy paste this helper. This is the helper that we used in the video about CPS. So we're going to insert it over here, and I probably should copy this one, right, and insert it somewhere over here. Right, so I'm gonna call it Fibonacci CPS with helper. Now we're not gonna use this helper in the rest of the video. I just wanna tie this video somehow into the previous one. So so over here, what we're gonna do is we're not gonna have the continuations like carried manually for us. We're just going to have the simple version as before, right? Without the stacks, without anything. So what we're going to have is we're going to have this loop like this. All right. So we just call it was an n and was nothing else. So then what we're going to do inside is we're going to basically pretend as if we're using CPS, but we're not actually using CPS properly, so to say. So we're gonna wrap the X in the CPS, and then we're gonna take it out. Remember, this is how we use identity. So the identity is always like sort of like the end continuation. So I'm gonna use it over here, and we're gonna use it over here. Actually, by now I'm starting to think that this version with the helper is going to confuse you more than you know, the actual the actual version with the continuations that we're going to write right after that. Okay, so let's finish that. So what we can do here is we can do CPS of x minus 2, and we have the first accumulation, right? And inside of it we have the second one. Just bear with me for a bit. And then we can loop with ACC1 and ACC2. And now this should work, but this is obviously not tail recursive anymore. Okay, too many arguments. That's not what I wanted. I wanted to add them together. This one plus loop this one, like that. All right, so now it says it contains recursive call targeting a supertype. Ooh, targeting a supertype, interesting. Oh, not this one. I wanted to mark this one. Oh, this one is automatically final. I'm just surprised that that the error message contains, you know, the error message is so specific. Oh, maybe I need to make CPS final. Hold on, final. No, I'm not sure why it's talking about a supertype. Because there are no, you know, supertypes involved here or whatever. In any case, it's not really tail recursive. Also, there is another version of this. We can also write it. First of all, let's run it. We're not even running it. Hold up. Let's put it over here. All right. So it's running. We could also do this. We can you know, we can sort of break the CPS version a little bit apart, right? So we can do like partly CPS, partly not CPS. So all the results are still the same. All right, so I just kept saying that obviously it's not tail recursive, but actually it's not that obvious. So the thing is that if you look at it closely, we're not calling loop from inside of loop, because technically we're calling CPS and then CPS calls loop, right? So we're passing this function to CPS. And what CPS is doing is it just calls this function, right? So what we ending up having is that CPS calls loop, and then the loop calls CPS, and then CPS calls loop again, and loop calls CPS again, right? So this is called mutual recursion, and mutual recursion is a very hard topic. So it turns out that on the JVM, it is not so easy, or maybe it's actually even impossible to remove mutually recursive calls. So what the Scala compiler can do for you is it can remove the so-called self-recursive calls, but it can't remove the mutually recursive calls. And this is going to be the topic of the next few videos. We're going to see what we can do about this. Right? For now, we're just going to leave it as is. And you know, we're gonna forget for a second that this is not tail recursive, but just keep it in the back of your head. This is the goal. The goal is, you know, to have things in a tail recursive way. All right, so same as for the previous example, you can go to the loop down there and make sure that it runs only for one value, and then you can make sure that you print out the ACC1 like this, right? I'm not gonna run this. I'm just showing you to, right? So you can print them both out so that you understand like how the flow of control works here, because it's going to get more and more complicated, and I can't invest like that much time into having like all of these print lines, because we have quite a bit of content that we have to go through today. All right, so as I said, like in the previous video, we wrote this helper, and now we're sort of using this helper, but what we need to do is we need to forget about it, and we need to figure out a way how to rewrite every function in a proper CPS style. And the proper CPS style means that we need to actually have loop in this form, right? So this used to be, you know, in the previous video, it started as an identity function, and then all of a sudden we said, oh, it's not now it's going to be an identity function that takes a continuation, that takes the result and puts the result into the continuation. So we need to do something like this with a loop itself. right? So what we want to have is something like this. So the thing is that it turns out that it is always possible, and it is always possible in the mechanical way. And this is exactly why we're doing this, because so far, you know, we had like factorial a long time ago, and then we had Fibonacci, and then with our sets we had, you know, add function and the fold function. And every time we wanted to make them tail recursive, we had to come up with some, you know, with some weird trick or some weird, you know, thing. We had to rewrite algorithm in a way that was not always obvious. And what CPS and also the technique that we're going to discuss in the next few videos is going to give us this mechanical way of rewriting. And it starts with CPS, because it turns out that you can rewrite any function mechanically into CPS. So the first thing that you need to do is you need to pass each function that you're talking about. In this case, we're talking about loop. You need to pass it a continuation, and a continuation is gonna have the type of the result type sort of mapped to the result type again, because this is what the stack was doing for us, right? It was carrying like one long from one stack frame to another, from one stack frame to another. And this is exactly what the continuation is going to do. It's going to take a long and it's going to produce a long, and then we're going to bootstrap this whole computation with the identity continuation, because as we already learned in the previous video, the identity continuation is basically the end continuation. This is how we start, and this thing is going to be in the end called like as a very last thing, right? So I just showed this first step to you, but in fact we should do something else. So I'm going to leave this one alone. I'm going to leave this one alone like this. Let's see if it works. It works. So we're going to go to the top. I'm going to take the original version of Fibonacci. I'm going to take that. I'm going to go down again. And now we're gonna end up here with Fibonacci CPS with helper. So we're gonna paste the original Fibonacci inside of here, right? And we're gonna call it Fibonacci CPS, right? So now we're gonna do what I just said, right? So we're gonna pass it. First of all, we always have to rewrite it into this version that contains a loop, because you know we don't want to ruin the API, right? So let me quickly rewrite that to a loop. We did this sort of thing many times, right? Long. So now over here, every time we use n, like this one, we're going to use x over here, loop over here, equal sign over here, and at the bottom we're calling loop with n, and I'm going to save that, and let's also run this version as the very last one over here, like that. All right, let's go back to it. Okay, it's over here. Right, so as I said, like the first step is always to add the continuation long to long, okay, and bootstrap the whole thing with the identity function. All right, like this. So obviously now if I save the file, it's not going to compile, right? And the next thing that we're going to do is we're going to wrap these in the continuation, because the second rule, so the first rule was, you know, you pass in the continuation. The second rule is every time you have an expression which doesn't contain a function call, so it doesn't contain the call to the loop, right? So it doesn't contain any recursive call. You just call the continuation, right? So you pass this into the continuation. Same thing over here. Continuation of 0, continuation of 1, like this, right? Or you can also say continuation of x, because it's, you know, x is 0 and x is 1. So you can do x, right? Same thing. The third rule is the most complicated and the most important one. It says that whenever we have a function calls which are not in tail position, you need to rewrite them by producing another continuation. So first you're producing another continuation, and then you pass it to the loop. And this is exactly what we're going to do here. So instead of this, I'm just going to comment this out. We're going to have a call to the loop, and I'm going to use named arguments this time. So I'm going to say, okay, the x is going to be x minus 2. Okay, and by the way, this is the same code as this, right? So we can swap them like this, 2 and 1. Okay, and the continuation is going to be what we're going to create now. So what we do now is we're naming the result of whatever would come back from that loop, because remember, this is exactly what continuations are about, right? You're passing in the function, and then the function is going to get the result. So this here is going to get the result of whatever comes back from loop, so to say. Okay, and because we're using Fibonacci, and Fibonacci has 2 calls to loop, we have to do this sort of thing again, right? So we have to call loop again over here. This time x is going to be x minus 1. Okay, and in fact, you know what? Let's not do this yet. Let's do the partial CPS version. So let's just do that. Let's just do ACC1 plus loop with the same continuation, right? Let's just do that for now. So I believe that already should compile. And did we include it already? Fibonacci CPS? Yeah, we did. Okay, so now it already works, but this is like a partial one. We could do the same thing. We can do the same thing with this loop. So I'm going to comment this out, and I'm going to say, okay, loop again, x equals x minus 1, and then the continuation is going to become a new one. So we're creating yet another continuation. I know that this is very confusing, right? And now over here we have ACC1 plus ACC2, but there's also a fourth rule. So I remember every time. Basically, the fourth rule is we're coming back to the first rule. So every time you have an expression which is sort of already in the tail position, but it's not a call, you have to wrap it in the continuation. So if you leave it like this, it's not going to work. I mean, it's going to compile, but it's going to produce weird results. So we need to call the continuation, the original one, this one. We need to call it over here. Okay. So you can use the same principles with the print lines here, but just the print lines are not going to be enough. Actually, you're going to see like this weird, really weird control flow. Spend a bit of time to to look at this and to understand this. All right, so I'm going to remove this. I'm going to remove that. Now, is this helping us? Right. So we have like the proper continuation style now, but does this mean that it's tail recursive now? Scala annotation tail rec. There we go. All right. So now it says could not optimize tail rec annotated method loop. It contains a recursive call not in tail position. Okay. So and it shows at line 105. So this one is not in tail position. This one is, but this one is not. Now again, this is mutual recursion. So the Scala compiler can do that. What I want to show you just real quick that the annotation has a tiny bug. So if we don't call loop from inside of loop over here, if we call a different function called blah, and blah will take a few parameters, right? And blah will call loop for us. Let's actually create it over here. So I'm gonna have def blah long continuation long. Right, so I basically gave it everything that it needs, right? So it needs the x, it needs the ACC1, and it needs the continuation, right? So just so that blah compiles. So notice that right now we're not calling blah. Hold up. Okay, so right now we're not calling it, but blah compiles. So as soon as we call blah, so we call it was x and ACC1 and the continuation instead of this. Right, the whole thing still works, but now the annotation becomes silent. Right, so this is the bug in the Scala compiler. It's been out there since Scala 2.11.1, I believe, and I'm gonna leave the link down in the description to the bug. Right, so but yeah, just know that it is basically impossible to remove mutually recursive calls in such a way, but we're gonna find a solution in the next few videos. So let me revert all of that blah stuff. So I'm just going to have that and that, and I'm just going to remove blah like this. So now it's not going to compile because now it actually doesn't run into this case where, into this bug. So so yeah, so we're back to the working code, but obviously we know that it's not tail recursive, which means that the stack is going to explode for very big inputs. The next thing that I'm going to show you real quick is basically exactly the same bug, but in a in a bit of a more obvious way. This is a very popular demonstration of this bug. So instead of this print line, we're going to do something else. So we're going to have two functions, is even and is odd, and they're going to be written in a very weird way. So we're going to say, okay, if it's a 0, sure, then it's even. Otherwise, if it's something else, then just call is odd with n-1, right? And is odd is going to be very similar, like that. Like that. So if the 0 is a false, otherwise is even, -1, right? So now what we're going to do is we're going to print out 0 to 10, let's do to 9. Map to is even, make string tab, and we're gonna do the same thing for odd. Right, so it basically goes down until the 0. So what we have now is a mutually recursive function, and obviously it's not tail recursive. Right, so if we add these over here, it's going to say, hey, it doesn't even contain a recursive call. Right, so it says tail rec, and it's a method contains, it doesn't contain a recursive call. It doesn't even see it doesn't even recognize this as a recursive call. So if we trick it into thinking that there is also a recursive call, then we will stumble on the bug again. Right, so where in is even, so we can do this is even, and we can even throw an exception here because this this thing is never going to run. Not gonna happen like this, and we're going to do the same thing over here. This time is odd. Right, so now the compiler is going to look and it's going to say what's happening. Exception, not going to happen. Did I make a mistake? So instead of that, let's do just is even 0, which is true, right, and is odd 1, which is true. All right, so now it compiles and runs with this annotation. Right, so if I remove that, it's not going to compile, right? Because it says it doesn't contain any recursive call. Well, okay, so I'm going to give you the recursive call. You're never going to call it anyway, right? But still, right? So we're running into the same bug. All right, so we're done with Fibonacci for today, but notice that continuations, they have this weird habit of not only inverting, but also like completely reverting the flow of control. And this is going to help us with the add function, because remember with the add function, we have this problem that we ended up needing basically 2 stacks. We said we want to go down to find the spot where we want to put the element, and then on our way back, we're rebuilding the element. So we're rebuilding the set. So continuations are perfect for this. And so now we're basically done with Fibonacci, and we're going to switch to testing. And let me go to the set. All right, so we're gonna go to the add function. Let's see, where's fold, add original. Okay, so this was the original add, and this is the one that we ended up having. This is the one that, you know, it finds out the path, and then it rebuilds the set based on that path. So what we'll do now is we're gonna write a better version that uses continuation. It's gonna be much shorter. Right, so what we're going to do is we're going to rename add to add stack, like this. Okay, and let's see. So let's duplicate this line and bring it. Okay, if I start bringing it down, it's going to unfold everything. So I'm not going to bring it down. I'm just going to cut it out. I'm going to paste that over here. So this is going to be override, and this is going to be add. Okay. So what I'm going to do here is, oh no, actually let's leave that. I'm going to take this path function and I'm going to paste it over here. Because the direction of path was correct. And now instead of carrying the path over here on the stack, we're going to carry the continuation. So our loop is going to produce the set of super, right? And therefore our continuation over here is also going to be same as with Fibonacci. It you know, takes a set of super, produces a set of super. Produces a set of super, right? And therefore we're going to bootstrap the whole thing with an identity, right? Identity. Okay, so in the default case, it was just returning the path. Well, now we just need to call continuation, the same as in Fibonacci, and we need to look at the rebuild, what the rebuild was doing, and how the rebuild start. Okay, rebuild started with this, so we need to take that. We need to put that over here. Okay, so if input is the same as element, well, we just call the continuation. By the way, these comments, we don't need them anymore. Continuation with the non-empty. Right, let me remove these comments. Remove the comment. Remove the comment. All right, so let's remove that, and let's remove that. All right, so this is the important part, right? This is where we're passing the continuation. And remember, the rule said every time you're in the call that was, you know, supposed to be a tail call, but it's not a tail call, it's an operand position, you just create a new continuation. So we're going to create a new continuation that calls the old continuation with not empty, copy, left equals ACC, at the bottom we have the right one, right? So this is the, like, this copy part was the part that rebuild was doing. So this was the rebuild, right? So remember, we had the add function, and then we were forced to split it into two because the directions were different, right? So the finding of the spot was one direction, rebuilding that path of the sat was a different direction. And this is exactly what continuations are good at. We can do the same thing at once. So we're saying, okay, we found the spot, but don't rebuild the path yet, but remember how to rebuild the path, right? Remember how to continue from right here. So unless I did any spelling mistakes, this is actually already done. Let's see. Oh, of course. Okay, so many, really. Okay, so first of all, let's call the path. Oh, we're still inside of path. We don't need that. Hold up. Did not notice that. So like that. All right, not found value sat. Okay, we're obviously starting with this. And there we go. Everything is still fine. Now I understand that this is kind of hard to understand. It's sort of easy it's sort of easy to implement if you used to continuations, but continuations are really mind bending, right? So take your time. The whole thing is going to be on GitHub. I want to point out a few things over here. It turns out that in the very beginning, we were also using continuation passing style. And when I say in the very beginning, I mean in the very beginning of this playlist. I'm going to actually open the browser. I'm going to go to commits, and I'm going to go to the very first version, which is over here, sats as math. So I'm going to click over here, and we can scroll down. And by the way, you can always also click on browse files, and then GitHub will show you the files as if they were in this version. So GitHub also has shortcuts. So if I press T, then I can start looking for the file. So I can type sat, and this is the file, and I click on that. Look, this was the original add function, the very beginning, before we had trees, before we had lists, before anything. Remember, we were saying, okay, sat is basically a function, and when we're saying add, we're basically creating a new continuation, sort of like a continuation, right? That still calls the old one, right? This was very similar to what we just did. Even it's very close to the is even and is odd thing that we just did, right? I just wanted to show you this. All right, so. The interesting thing is that if we start playing around with it, so if I go to Fibonacci again, right, and I'm going to say that this is Fibonacci, I'm going to create another one. Object yme extends app. So what we're going to do here is we're going to create a sat of 0, 1, 2, 9, 9, 9, 9, 9. Okay, so we're trying to create a sat with 100,000 elements. And because it's tail recursive, it should be fine now, right? So now it's going to run the test real quick. All right. Okay, so let's run yme. Okay, so it's starting to run now, and our code says that it is tail recursive now because the continuation is in the tail position, right? Notice that this time, like, nothing was there to complain. However, we still have a Stack Overflow, and this is what we're going to talk about in the next video. We're going to try to understand what exactly is happening here. Okay, so we still have a bit of time. I wasn't planning on doing this, but let's throw this one out real quick, and let's go back to tests. Because add and remove are so close to each other, so we can do this. Just paste that and just say remove. And we shouldn't forget to call this one remove stack. Is this how I call the add? So there's add and there is add stack. Yes, so we have remove stack. Okay, so remove stack, and this is not an override anymore. I want to keep all of them. Okay, so this is the one that I just copy pasted. It looks exactly like add, and I believe we need to change only that. This is the empty case, and this is the left union right case. And I believe that this is already remove. Yeah, the test is still green. All right, so we're done for today. All that is left is basically just to commit everything that we have so far. And we're not gonna do fold today or any others. If you want to do fold, start with the Fibonacci version. Was the helper, and progress from there. So basically start with the Fibonacci helper version, and then remove the with the CPS helper version, then remove the CPS helper a little bit, and just keep going from there. But fold is not going to be so easy actually. All right, so that's what we have now. We can actually push that, right? My key. There we go. All right. There we go. Okay, it's pushed. So it's a bit weird that, you know, we're moving through the continuations, and the whole purpose was for the continuations to help us out in this quest of basically eliminating the tail calls. And now we actually ended up with a situation where we have the continuation, and we have a continuation in the tail position. The annotation says that everything is fine, and in the next video we're going to see if it's related to the same bug as I showed it to you or not. Sneak peek, spoiler alert, it's not. All right, it's kind of weird. So we're gonna see though what we can do about this in the next few videos, and that's all I got for you today. It's been Vlad, devinsideyou.com. Like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.